Okay. So, in the last class, we discussed Hermitian transposition of matrices, that is conjugate transposition. As we first conjugate, take the complex conjugate of each element and then transpose the matrix, or first transpose the matrix and then take complex conjugate. And it was denoted by a superscript capital H, Hermitian transposition. When the matrix is real, it becomes usual transposition, conventional, ordinary transposition, which we denote by a superscript T on the matrix, right? Now, today we will consider a very important class of matrices called Hermitian matrices. Which also can be called conjugate symmetric. We know ordinary symmetric matrices in the case of real elements. Here is conjugate symmetric. Okay. Given say M cross N matrix A, it is Hermitian if A matrix and its Hermitian transpose, they are same. Okay, that is, if you take A, conjugate every element, then transpose whatever you get, that is on the right hand side, on the left hand side A, and if they are same, then A is called Hermitian. Okay. Now, you see LHS left hand side is a M cross N matrix. Right hand side, because there is a transposition involved in the Hermitian transposition, it will be N cross M. And since they are equal, and M cross N matrix and N cross M matrix, they are in general not equal. They can be equal if N equal to M. Okay, here I have got M number of rows, and here I have got N number of rows, and they are equal, the two matrices, they are same. That means M must be equal to N, which means Hermitian matrices are square matrices. Next, suppose I take LHS, left hand side of this, I find out its I comma jth element, and right hand side also I comma jth element, and then the two matrices are same because of the equality. So, I comma jth element on the left hand side, I comma jth element on the right hand side, they are same. But I comma jth element of the left hand side is nothing but Aij, ith row jth column, that element. The usual matrix notation, A matrix, ith row, jth column, that element is I comma jth element Aij. And RHS, I comma j will be, first there is a transpose, okay, and then conjugate. So, transposition means current I comma j after transposition is j comma I before transposition. Forget about this H. If I just give you an ordinary matrix, real matrix A, you take its transpose. So, I comma j in the element goes to j comma ith position, and j comma ith guy comes to I comma jth position. So, right hand side after the transposition, now I comma jth will be original matrix, its j comma I, and then a conjugate, because Hermitian transposition. So, it will be A j I star, and these two are same. That means, in this case A I j, because of the equality, the two matrices are equal. So, I comma jth element on the left hand side for any I any j will be same as the I comma jth element of the right hand side. That means, Aij and Aji, they are conjugate of each other, and that is why it is called conjugate symmetric. I comma jth position and j comma ith position, they are conjugate of each other. Like, you can take a matrix, say, and one more thing, if it is I comma ith element, j and I are same, that means Aii and again Aii star, they are same. And that happens when this is real, because a real number and its conjugate they are same. And I comma ith element means ith diagonal element, which means every diagonal element of a Hermitian matrix is real. Diagonal element, sorry, Hermitian or real. So typically a matrix, say a 3 by 3, it has to be a square matrix. So a 3 by 3 element, 3 by 3 a 3 by 3 matrix, Hermitian matrix, and just as an example, diagonal elements are real, they could be anything, 1, -1, 3, like that. Then 1, 2 and 2, element 1, they are conjugate of each other. So if it is say maybe 1 plus 3j, it will be 1 minus 3j. If it is then 1, 2, 1, 1, 1, 2, 1, 3, row 1, column 3. If it is minus 2 plus j. So 3, 1, 1, 3, first row, third column, and first row, third column, and now third row, first column, this, they are conjugate of each other. So it will be minus 2 minus j. And again, second row, third column, and third row, second column, these two are conjugate of each other. So if it is suppose j, it will be minus j, like that. This is a typical example of a Hermitian matrix. All right. Then, now before I go into this Hermitian matrix, why you are doing the Hermitian matrix, let's come to that. Last time I was doing, then I took a branch, I went into this side, Hermitian transposition and all. Now consider P complex, in general complex, because that takes care of real also, complex valued, continuous, random variables x1 xp with mean mu1 mu p. Last time I wrote mu x1 mu xp, just I am making it simpler, mu1 to mu p, because there is no other y or z random variables here, so it is fine. Okay. Then you from this vector, incremental vector x1 minus mu1. So mu1 is the mean, x1 minus mu1 is the increment or decrement around the mean, x2 minus mu2 xp minus mu p. You can give a name small x, maybe tilde. All right. And that is equal to this. So they are also random because B1 is constant. So this is increment, can go in the up direction or below direction. But this is random because x1 is random. So these are random increments or decrements. Okay. And now I define this covariance matrix C. Maybe xx was expected value. I am not writing anything on the subscript. You know, whichever random variable comes under the under this operation, only those variables will be part of the subscript, others drop out. So that is up to you, and now I think we have done it enough. So you yourself can work it out which random variables will come when. So I am not writing anything here. It is, suppose I take x tilde all right. So typical I comma jth element x tilde is this column vector, x tilde h H means first, it's a Hermitian transposition. So you take the transposition, means column vector becomes row vector. Okay, and then it's like this, x tilde, as it is you put here, and then the column vector, a row vector, x1 minus mu1 dot 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 xj minus mu j, xp minus mu p. If you want, you can even make it this way. You write the full of this x tilde here. This x tilde Hermitian is this, transposed and then conjugate. I have to put a conjugate on them. xi minus mu I all right, and then expected value. This is the meaning of this. So, this column vector into row vector, it is a matrix, and then you have to apply E on everybody. If xi and xj they are present in the ith row, jth element, jth column of this matrix will be what? This element times this element, because that is how they are from now. This into this will be the first guy, ith row, first column. This into next will be ith row, second column. This into this will be ith row, jth column, and so on and so forth. So, these two multiplied and E will have only xi and xj in the subscript, other variables will drop off. Okay. That means Cxx I comma j will be what? E xi minus mu I, this fellow, and this xj minus mu j star. This is nothing but covariance between xi and xj, two random variables. Okay. You take the increment around the mean, this into its conjugate, expected value. By definition, there is a covariance between xi, xj. And by the same way, Cxx, if you take j comma I, it will be xi, sorry, it will be maybe xj minus mu j, this times xi minus mu I star, j comma I. So, I and j, their roles are just interchange. Xj minus mu j come here, no conjugate, and xi minus mu I goes here with conjugate. All right. So, therefore, if I take conjugate of this, suppose I take conjugate, complex conjugate of this, what happened? The entire thing here have to apply conjugate. But we have already seen earlier in the case of complex random variables, E of some function of the complex variables, then star outside is same as E of the function its conjugate, like E, you remember Ez, if z will be vector of complex random variable, fz. Okay, and then if you put star, fz conjugated, then Ez, it will same as original Ez fz and then star. So, it is like this, fz star, fz was, okay, fz is what? You can write it as, there is no star here, right. So, you can assume as though there is a star and outside there is still a star, star cancels. And if you call this random variable z1, if you call it z2, z1 star, z2 star means z1, z2 star. Okay. So, expected value z1, z2 star, it will be same as expected value first z1, z2 outside star. So, it is like expected value z1, z2 is this much, Z1 with the star, first inner star, Z2 this much, then star is same as expected value of these two guys, then outside star. Okay, so xi minus my star goes out of it, and here xj minus mu j, there is a star. Okay, but this quantity is same as what we have here, xi minus my, xj minus mu j star expected value, that is what we have. So that is nothing but Cxx I comma j. So that means this matrix is such, its j comma ith guy and I comma jth, they are conjugate of each other. So that means it's Hermitian. I comma jth conjugate symmetric, I comma jth element and j comma ith element, they are conjugate of each other. Okay, so it is Hermitian. And when I and j are same, they are real, you can easily see, because if I and j are same, I comma I, it is xi minus my, again xi minus my star, which is mod of xi minus my whole square, which is real, not negative, and expected value of that, which is the variance. So diagonal elements are real, and in this case, not only just real, they are in fact non-negative, they cannot be negative, because mod of, if you take j equal to I, xi minus my star. So it is mod of xi minus my whole square. So mod is real and then square, so it cannot be negative, either 0 or positive, and expected value of that, which is variance. Okay, xi minus mi mod square is the power of the increment xi minus mi in a particular trial, when you got xi minus mi, and now you mod square, and then you are averaging expected value. So there is the average power, which is variance, and variance is real, non-negative, because there is a mod square inside the expectation. Okay, if this guy is mod square, expectation cannot make it negative, because expectation means what? You have to multiply by the joint density, which is again non-negative, probability density cannot be negative, dx dy, the dxi dxj, say an integral. Okay, xi means actually you have to take the real part, imaginary part, real part, imaginary part, so 4 times integral. But that is again, that cannot be negative, because probability density is non-negative, mod of this xi minus mi square. Okay, it will be actually double integral, because you have not xj, you have got xi only. So mod xi minus mi square, xi has two components, real and imaginary. So you multiply this by the joint density of the real part, imaginary part, and double integral. So this cannot be negative, because mod of xi minus mi square under the double integral non-negative, can never be negative. Joint density cannot be negative, the differential, dxi d of the real part, d of the imaginary part, they cannot be negative. So this is not only real, Hermitian matrices require this to be real, but it is not only real, in the case of covariance, they are also non-negative. Alright, so covariance matrices are Hermitian matrices, and in fact mean is 0, it will be just a vector x1 to xp and its Hermitian transpose, expected value of that, and that is called correlation matrix. That is, if you just take x1, x2, xp, call it x, then this correlation matrix is expected value of just x, no subtraction of mean. When the mean is 0, both the terms are 0. By the same logic, this is again Hermitian. Okay. You can take I comma jth and j comma I, they are conjugate of each other. This is called correlation matrix. Of x. This gives you the motivation for why you are going for Hermitian matrices. All right. Now, Hermitian matrices have some beautiful properties. We will next study them. Given A is a n cross n square matrix, there is a n cross n or m cross n or whatever, Hermitian, meaning if you take Hermitian transpose of it, conjugate and transpose, you will get the same matrix A. Also, give him A is an invertible matrix. See, all matrices may not be invertible, but in this example, suppose A is given to be invertible. That is, its determinant is non-zero. You can find its inverse. That is, A inverse exists. Then A inverse also Hermitian. This is a claim. I show it. If it is Hermitian, that is, if you take A inverse and its Hermitian transpose, you should get back the same A inverse. So this matrix is Hermitian transpose is A inverse. This is a claim we are making and easy to prove. Suppose I take A. A is given to be Hermitian. A and this A inverse H. There is no underscore here. This I can write as A is nothing but AH, because AH is A, and then A inverse H as it is. We have seen ABH is BH AH. We can go in the opposite direction. If it is BH AH, it will be ABH. So it's like BH AH. So it will be ABH. It will be A inverse, which is taking the role of A. A inverse is taking the role of A here, AH. AH, A is taking the role of B here. First guy is B. BH, second guy is A. So BH AH means ABH. So this comes first, this goes here, H. And A inverse A is identity. Identity is already Hermitian. All the diagonal entries are 1. They remain there after Hermitian because I comma I after transposition remain at I comma I. So diagonal entries remain 1. If any I comma j element is 0, because it is identity matrix, after transposition it will go to j comma I, and conjugate has no meaning, 0 is real, so it will become 0. So identity matrix, if you take its Hermitian transpose, it remains identity. Zeros from I comma j go to 0 I j comma I, and zeros from j comma I go to I comma j. And diagonal matrix, diagonal elements remain same, 1 1 1, so it remains identity. Now, in matrix theory, we already know that if I give you two square matrices, so A and if you call it B after the Hermitian, if A, B both are square matrices, product is identity, then one is the inverse of the other. So B is A inverse, A is B inverse. So that means if I write B, that is same as A inverse, because AB identity means one is the inverse of the other. B is inverse of A is inverse of B, ABI. So A inverse is I, or A inverse A is I, or B inverse B is I. Okay, and this proves what we wanted. A inverse A is same as A inverse. So inverse of a Hermitian matrix is Hermitian also. All right. Okay. Another thing, if X is a n cross 1 vector, may be complex, A n cross n Hermitian, then if you take this quantity x h a x, A times x, x is a column vector, x is a column vector, A is a matrix, A into x is a column vector, xh is a row vector because x was column. So, after transposition, Hermitian transposition has a real transposition plus conjugation. Transposition, it became row, ax is a column, so row into column is a scalar. It is not a matrix, it is a scalar. So, this our claim is this is a real scalar. Even if x is complex, A has complex. How to show? Any real number is what? If I take complex conjugate of the real number, I should get back the same thing. Then only it is real. Okay. If x is a real number, then x star is same as x. Now, here left hand side, if I take star, is a scalar star. Now, here is a trick. Any scalar also you can view as a 1 by 1 matrix. If I give a scalar number, say alpha, it is a scalar. It can take 2 or 3 or j or whatever value, but scalar. Any scalar number is also a 1 cross 1 matrix, like a n cross 1 n matrix, n columns, n rows. It is a 1 cross 1 matrix. Okay. So, 1 cross 1 matrix. So, this I can also write as, let me first write H, because if it is a 1 cross 1 matrix, H will be in first transpose, but a 1 cross 1 matrix after transposition remains as it is because only one element, and then conjugate. So, there is a conjugate I want it. So, I can make it, instead of writing star, I can put H here because it is a 1 cross 1 matrix. 1 cross 1 matrix on only one element. So, if you take transpose of that matrix, you get back the same matrix, then conjugate. All right, and conjugate is what I have already put. But now I know ABH is BHH, and that is what I will write here. Suppose this is your A, this is your B. So, it will be AX H, AXH and XHH. XH H will be bring back x because x was a column vector. Now, XH will be row vector with conjugates. Again H will make it further column vector by transposition again, and conjugate on conjugate will remove the conjugate. So, you will get back x. And here again ABH is BHAH. So, it will be your XH AH, and here it is x, but A is given to be Hermitian. So, AH is same as A, this AH is same as A, which is XH AX. So, that is what this is. So, this scalar, its conjugate is same as the scalar itself. The scalar's conjugate is same as the scalar itself. So, this scalar is real. So, in subsequent lectures I might use this kind of expressions and we will take it to be real. So, you understand why it is real, provided A is Hermitian, AH is A, otherwise not. All right. Now, next I will go to what is called eigenvalue and eigenvector, which is a new topic. So, that I will do in the next lecture. Thank you very much.